Okay, my name is Julia Cornwell, and we are going to talk about Ohm's Law. Ohm's Law is pretty simple, really. It is best represented by this equation, V equals IR. So to understand what those variables mean a little better, V is the difference in electric potential between two places, and that's measured in volts, and that's equal to the current times resistance. And the current is the flow of 1 coulomb of charge per second. So basically how much charge is flowing, and that's measured in amperes. And then resistance is measured in ohms, and we're going to elaborate on that a little bit more in a minute. So this equation shows us a couple things. First, the current is directly proportional to voltage. So you have a voltage source, like a battery is a common one, and that drives a current. And as that voltage goes up, the current also goes up. But on the other hand, current is indirectly proportional to resistance. So as your current goes up, your resistance has to go down. Or as your resistance goes up, your current goes down. So now to understand what resistance is, it's clearly an important part in Ohm's law and really affects it. So we want to understand what is a resistor. And literally what a resistor is where charges in the current collide with atoms of the substance carrying that current. So, and then it therefore impedes the current. So I like to think of it, we know from previous physics that when two objects are touching that there's friction between them, and friction causes something to either slow down or to not move. So I like to think of resistance as kind of like the electrical form of friction. And resistance increases with temperature. And there's a lot of common examples. A light bulb, like a headlight in a car connected to a circuit, is a resistor. And certain materials also provide resistance, like wood and rubber and others. So we're going to look at an example to apply this a little bit more to us. We're going to look at an example of skiing. So I am like the little skier here, and I'm representing the current. We're going to say that I'm like a charge of current trying to move down the mountain. So the mountain is going to be our wire carrying that current. So we're going to watch this video first, and it's just kind of a foundation video to understand what we're looking at. So there I am moving down the mountain. But now we're going to change a couple things. We're going to say, let's say it's been a really cold day, and so the snow is really icy, and it does not provide a lot of resistance. So now what happens to me as a current? So if you can see, kind of small, but if you can see, I move way faster down the mountain. And now we're going to say, let's say the opposite happens. There's tons of snow, it's super fluffy and powdery. Then what's going to happen to me as a skier? So as you can see, it's taking me way longer to move down the mountain. So my point with this was to show kind of different circumstances we have. If we're saying that I am the current, I'm like a charge trying to move. If there's little resistance underneath me, then I can move really fast. And so let's say there's a bunch of skiers on the mountain. In 1 second, several skiers can pass down the mountain if it's icy and there's little resistance. On the other hand, if there's a lot of resistance, then in 1 second, not very many people can pass down the mountain. So same thing in a circuit. If there is a lot of resistance, not a lot of charges or current can get through or can move quickly. So now applying this to a physics example, it says here, what is the resistance of an automobile headlight through which 3 amps flow when 12 volts are applied to it? So we have a simple circuit drawn here to our right, and it shows us the voltage that supplies the current, and then we want to find out how much resistance is affecting that circuit. So we'll use our equation that we talked about, V equals IR, and it's pretty simple because it tells us that V equals 12 and we know that our current is 3, so we plug those in and we get resistance equals 4 ohms. So that's a simple way, but that's how we are able to find how much resistance or current or voltage is involved in a circuit. So now we'll look at a slightly more complicated example here. We are asked how much current flows through this circuit. And we're given a circuit drawn on our right, and it's a very similar circuit as the one before, but this time we have 3 resistors. So we have R1, R2, and R3. And these resistors are connected in series. That just means that one comes right after the other. And so with that, all we have to do to get our total resistance is add those 3 resistors together. So we're going to use our equation again, V equals IR, and our voltage is 12, our current is what we're trying to find, and then R is the sum of those 3 resistors. So we're going to add 10 plus 20 plus 30. And when we add that, we get 60, we divide 12 by 60, and we get that the current is 0.2 amperes. So that's how we'll use resistance and Ohm's law mathematically. And now back to talking about it a little bit more conceptually. We know that there are a few things that affect Ohm's law that will affect the resistivity, and that is the shape and the material that it's made of. So if you have a wire made of certain material, that'll either provide more resistance or less resistance, and whatever shape it's in will also affect it. We can apply this again to our skiing example, where if you have skis that are a certain shape or they're made of a certain material, that's going to affect how fast you're able to move. So in summary, this is a picture of George Ohm, who wrote Ohm's law, and what it basically teaches us is the relationship between voltage, current, and resistance, and that allows us to understand our electrical world a little better. Thank you.